This lesson deals with supplemental problem 811. You can find this problem in the ECE202 ebook in the Chapter 8 supplemental problem starting on page 11. Let's take the circuit from supplemental problem 810 and let's simulate it with PSpice. Let's plot the magnitude of the impedance, the magnitude of the voltage across the L and C, and the magnitude of the voltage across the capacitor versus frequency. Let's sweep it from 0.6 Hz to 6 kHz. In other words, 2 decades below and 2 decades above resonance. Okay, let's take our circuit with our values. Label the nodes. I'll call this 1, 2, 3, and ground. And let's describe our circuit. Need a title, need a dot end. Our voltage source is between nodes 1 and 0, plus sign, minus sign. Has a value of 170 at angle 0 as a phasor, and you got to say AC to indicate it's an AC analysis. If you leave the 0 off here for phase angle, it's defaulted to that value. Our resistor is between nodes 1 and 2, has a value of 10. Our inductance is between 2 and 3, and has a value of 703.62 millihenries. And our capacitor is between 3 and 0 and has a value of 10 microfarads. Need dot probe to get the graphical output. And then let's sweep our frequency in decades from 0.6 to 6 kilohertz. And let's put 200 points on the screen. So if we take the 4 decades that are here, divide that into 200, you get 50 points per decade. Take a look at the results. Now, impedance is not one of the things you can click on in the probe part of PSpice, but you can plot voltages and currents. So let's take the magnitude of this voltage divided by the magnitude of the current coming out of the source, and that would be the current in the resistor because I defined it for between nodes 1 and 2. Now the current is defined going into the plus sign of the voltage source, although for magnitude we wouldn't see any different result, but for phase angle it would make a difference. Let's take a look at that then. So the magnitude of the voltage at node 1 divided by the magnitude of the current in the resistor R. And you can see here I've got a minimum value at 60 Hertz, and the value is equal to 10 ohms. Now why is that happening? Well, at low frequencies, the capacitor looks like an open circuit, and the inductor looks like a short circuit. So as the frequency gets lower and lower relative to resonance, the value of the impedance goes up. And you can see that with this line. Now 0 Hertz is really at minus infinity here. It just keeps increasing, but you can see it's an increasing value. Our scale is really a log scale, and so we're just going smaller and smaller as you go back in frequency. The same thing happens above resonance, but now the inductance looks like an open circuit and the capacitor looks like a short circuit. In other words, j omega L, when omega gets very, very large, begins to be nearly an open circuit. And then minus j of omega c, as omega gets larger and larger, no matter what the value of the capacitor is, it gets smaller and smaller. So as the frequency increases, we have a resistance, nearly an open circuit, and then again nearly a short circuit. So you see a very, very high value of impedance. Now at resonance, these two cancel and you see the 10 ohms. And sure enough, there it is. I mark the X and Y axis. So here's my 60 Hertz and a value of 10 ohms. We saw a maximum current at this frequency because the impedance was its smallest value, because the real part doesn't change with frequency. Yeah, it's kind of unique to this particular circuit, and actually one more called the parallel resonance circuit we'll look at the next supplemental problem. Now let's take a look at the voltage across the L and C combination. Here's node voltage 2. You can see at 60 Hertz it looks like 0. At low frequencies, we're seeing that the voltage across the series combination is basically the input voltage of 170 volts. And the reason for that is because the inductance looks like a short circuit and the capacitor looks like an open circuit. The voltage divider basically that's approaching 1. Same is true at high frequencies when the capacitors are short and the inductor looks like an open. We call this a notch filter. We'll take a look at this in chapter 12. This is used for some interesting tuning circuits. Look at any other voltage and current because we can do that in probe. Here's the voltage across the capacitor, and you can see here at 60 Hertz is a very large value of voltage. It's 4.5094 kilovolts in magnitude, and it's pretty much what we calculated by hand. At low frequencies, the capacitor looks like an open circuit, and the inductor looks like a short. What you're seeing here is just the voltage of the source, which is 170 volts. It's on a much larger scale here. As the frequency gets higher, the capacitor looks like a short circuit, and there's no voltage across it. So you can look at the formulas that we derive, but you also look at the picture and the schematic and begin to actually argue some of the endpoints or points of interest. Now this is supplemental problem 811.